Hello to anyone watching the live stream or the recording. We'll start up in about 5 to 10 minutes. So, yep, just skip ahead 10 minutes. Thank you. Yeah, and you're on the live stream right now. So you're partly in shadow.
Well, it doesn't have to be green to be on the live stream.
No, red. Red means live stream.
Red is dangerous.
Yeah. Why are you in shadow just there? That doesn't make a lot of sense.
Why am I in shadow just there? I'm lit up from here up.
Yeah, you are. Ah, that's from there. Yeah. You can't post it.
Shadow so much. It's light this much.
Yeah, not as in light as it. Okay. So, Chris, thank you for doing the live stream today, the presentation. Has it been good fun preparing?
Yeah, it has been a very rushed blast.
Okay. Well, I'm sure it's going to look fantastic.
It's going to go, thanks. Here we go.
Cool. Zero on the live stream.
All good, all working.
Seems to be.
Still short some dongles, but okay. I'll stand there by the laptop to get the space bar. Many slides. Yes.
What do you live stream? And you can hear something. Yeah. At one point, I could hear it, and I was like, okay, yeah, that's they're not very three or four flights. I've had better solution. Oh, it was and he's got this 5-year-old crying in the background. He says, "Oh, I'm sorry, I thought this was another lawyer." His wife burst out and then another one came out and tried to do it again. It's like,
So, yeah, Chris, welcome and thank you for doing today's talk. Over to you.
Okay.
Hello everyone, grab a seat please.
So hello, and welcome to the Ethereum Engineering Meetup for August. Well, the first one for August, and then we did this every 2 weeks. So my name's Chris Mackay. I'm an engineer at Consensus, and I'm here today to tell you a bit about how the Ethereum virtual machine works and how that impacts the rest of the Ethereum ecosystem. So before I jump into it, Some assumptions about the audience for this talk. First of all, I'm assuming that you're all familiar with some basic programming concepts, so things like loops and variables, and the sort of things you write in Java and such like that. Second thing I'm assuming is that you're not too familiar with low-level computer architecture. If you are, the first half of this talk is going to be pretty boring, so I apologize for that. And thirdly, I'm assuming that you're comfortable with a bunch of Ethereum concepts, such as transactions and accounts, and that this thing called gas exists. And I think that one's a pretty safe assumption because this is an Ethereum meetup. So, first question we should probably have then is, what is the EVM? And on the blockchain, at any given point in time, we have a world state. And I apologize for my diagrams, they're all a bit dirty and disgusting. If you can't read anything, pull me up on it and I'll read it for you. My handwriting is about as appalling as the diagrams. So on the blockchain at any point in time, there is a drivable world state which contains a list of accounts that exist on the chain, the storage which is inside of those accounts, and potentially any code if they're contracts. And what the EVM acts as is a mechanism for incoming transactions with their message data to take the old world state and transform it into a new world state after applying the actions described in that transaction. As a more formal explanation, the Ethereum virtual machine is a simple but powerful Turing-complete 256-bit stack-based virtual machine that allows anyone to execute arbitrary EVM bytecode, which is quite a mouthful and more or less explains what this talk's all going to be about. To make that less of a mouthful and to give us some understanding of what that means, we're going to spend a lot of time today looking at what the stack-based virtual machine is and developing a good mental model of that. And then we're going to try and apply some of the Ethereum concepts that exist out in the world back onto that mental model so we can understand what's being said when people say that transactions consume gas. So first of all, what's a stack? A stack's a data structure. It's a last in, first out data structure. Values go onto the stack, they get added to the top of it, and values can be taken off the top of the stack. You can't read from the middle of the stack and you can't read from the bottom. And even saying read is a bit of a misnomer. You can consume values off of the stack rather than just taking a look at them. So you have to be careful that you're not going to accidentally use something that you're going to need later. So that's a nice data structure. How do we use it for computation? Well, we have operations which know how to act against the stack, and these operations take their arguments from the stack and return their results to the stack. The operations can take a variable number of arguments and return a number of variable arguments onto the stack, and they can do things such as basic arithmetic, or slightly more complex arithmetic that has the same sort of operation profile. They can treat data in different ways. They don't always have to treat it as numbers. They can treat it as binary values, or they can treat it as addresses, depending on the context of the operation. And not every operation needs to be taking arguments in. Some of them visit out to the environment and bring things onto the stack. And subsequently, not every operation you perform is going to be returning a value onto the stack. Some of them just consume and affect the environment around the virtual machine. So those are instructions and operations that we can perform. We need to assemble these into a program somehow. And to do that, we have punch cards. Traditionally, you come along with a hole punch and you plug in a representation of the operation you want the computer to perform. And once you've marked everything out on your punch card, the computer comes along and scans a read head along the card. It interprets what the first instruction is, asks the machine to apply it, waits until the machine's completed applying that instruction, and then the read head moves along, and the next instruction goes through the same process. And it keeps on doing this until it gets to the end of the program. Thankfully, we've evolved a bit since then. We no longer have the physical medium for this. Instead, we've got lists of bytes being stored on the disk, which are being read with the program. Beyond that change, though, the paradigm stays much the same. The program starts at the first byte in the list and starts moving through the bytecode until it reaches the completion of the program. It passes this binary representation into the machine, applies the changes that it's asked for, and then moves on to the next instruction. And it keeps on going through the instructions until it reaches the completion of the program. A big difference from the physical medium, though, is we no longer have a reader head to represent where we're up to. So instead, we have a register that stores which stores the address of the current instruction that we're up to, and this is called the program counter. And just like the read head, when we move from instruction to instruction, the program counter moves forward with us. Now, this binary code doesn't make much sense to us as developers. There are some people who are happy to read it. I'm definitely not one of them. So to make things more sensible for us, we label these instructions with logical names that represent what they do. And now we don't have to have an aneurysm every time we work on it, and we can start to read this a little bit as code. So let's work through this example a little bit and get a feel for how a stack machine does computations. So the machine comes along and it looks at the first instruction, and we've got a push instruction. A push instruction adds a value onto the stack. And in the case here I'm using push 1, and in the EVM, push 1 pushes 1 byte of data onto the stack. You can push up to 32 bytes of data at a time. And it needs to know what to push. That's not included in this instruction. So the program advances forward looking for the data that it needs to use for push. It moves forward and it finds 1 byte of data and treats that as the argument going into the push. And it adds that to the stack. That being done now, yep.
So if you're trying to add 32 bytes, is it push 32?
If you try to add 32 bytes,
how many opcodes are there?
There is about 127 opcodes.
Right.
All this comes much later in the talk about the specs of our specific machine.
I pushed them about this.
There's 32 of them.
Are there really? Okay.
Yes, there's push 1 through push 32. And push 32 just steps through 32 following instructions to get to 32 bytes of data.
Thank you.
So, the push being completed, we then advance on. We have another push, so we can't act yet. The machine moves forward and sucks up the piece of associated data and puts it on top of the stack. And now we've got 2 and 3 on the stack. Then we've had the instructions say that we've got to perform an addition. It looks at the stack to get its arguments now rather than looking at the bytecode. It grabs the 2 values off of the stack and adds them together and returns the result onto the stack for further usage by later parts of the program. After that, we're adding more data to the stack for another push. That appears on top of the stack next to the result of our addition. And then we're going to multiply them together. And just like addition, it sucks in the 2 arguments from the stack and returns its result onto the stack. Having the separation of the push from the computational arguments is a very clean segregation between the data handling logic and the computational logic, and leads to a bunch of beneficial factors that we'll talk about later that help in the Ethereum ecosystem. And this bytecode here represents the code at the bottom of the screen. Add 3 and 2 and then multiply by 4. A very small line of code that blows out to a whole bunch of instructions. Gets very verbose really quickly. To save on some of that verboseness, we're going to do a simplification for convenience. Where a opcode is taking an argument, we're just going to put it in parentheses rather than explicitly putting it in the next instruction location. So all that being talked about, we now have top-down execution going through a program, and that's cool and all, but that's not super useful. We need our programs to be able to have control flow and be able to do loops and stuff. And for that, we need to be able to jump. So let's look at an example where we jump. First thing I'm going to do is I'm going to push a 0 onto the stack, and I'm going to use this as an accumulator. It's not going to have any impact on the jump, it's just so that I have some sort of logic going on here aside from the jump so we can see the paths that are related to the jump as opposed to other computational efforts that we might want to make. And this accumulator is something that we're going to be adding data to. Second instruction we reach is a jump destination. You need to declare these on the stack, or you need to declare these in the virtual machine. You can't just jump to arbitrary positions, otherwise the virtual machine starts to think that you've made a mistake and it's going to throw an exception on you. But you declare places where it can land and it makes sure that you're safe in doing so. There's no particular side effects of the jump destination other than registering itself inside of the virtual machine. That being established, we then move forward and we push a 3 onto the stack. We add it to our accumulator, so we're counting up in 3s. And then we get down to pushing another value onto the stack. We're pushing a 2 here because the 2 is the address of the jump destination that we want to go back to. So a jump can go to an address, so long it's also been declared as a jump destination. Jump, like almost every other operation you perform against the stack, takes its arguments from the stack, not from the bytecode. So you take the address of 2 into the jump, it pushes that address into the program counter, and the program counter makes sure that that address number 2 was a jump destination. And then the program can progress forward just fine from instruction number 2. It goes through pushing the 3 on again, adding it to the accumulator, counting up by another 3. We push our jump address on again, and then we jump again. And execution continues on doing these mundane things until we get down to the end again. And that's great and all, and it's kind of useless. This is an infinite loop, which isn't super useful to anyone. And it's more or less that useless while loop below that just keeps on counting up in 3s until the universe ends. It'd be much more useful if we could get out of the loop somehow. So let's see if we can make this loop conditional. New example. These examples are getting more and more complex, and I'm trying to build up towards having a more complex sense of how data gets shuffled around on the stack as you're using it. And hopefully that will come across throughout this talk. And I'm also going to speed up a bit and start performing multiple steps at the same time for steps that we're already familiar with. So for this example, the first thing we do is we're pushing 2 values under the stack. A 0 is our accumulator and a 2 is our loop counter. I'm going to keep the loop counter mounted with an asterisk in the stack diagram so that we can keep track of it more easily. We then establish our jump destination like we did before. Then we get to another new instruction, swap. Swap is used for reordering elements on the stack and bringing things to the top. In particular here I'm using swap 1. It looks 1 level down on the stack, reads off everything that's above that level, and then rewrites them all into the correct order. There's versions of swap which reach up to 16 levels deep in the stack, making the first 16 values on the stack available to the program at any given point in time. And this sort of dancing around of values becomes very common in a stack-based machine. So we're doing a swap here to bring the accumulator into focus because we're not going to be using the jump counter. We're not going to be using the loop counter yet. We're going to first of all be doing something with the accumulator. Namely, we're going to be adding 3 to it again. So we push 3 on top of it, tell the machine to do an addition, and it does that and returns that to the stack. Then we get down to another swap to bring the loop counter back into context. So now that that's in the top, we've got to decrement the loop counter so that we know that we've completed this iteration of the loop. So we push 1 onto it because we're going to want to decrement by 1. Then we have to swap these around because the order of arguments matters to the operations that are being performed. And 1 minus 2 isn't the answer we want. 2 minus 1 is. So we swap around to bring the loop counter to the top. And then we're able to perform the subtraction that we wanted. Now we have another new operation, duplicate. Because you can't read from the stack, you can only consume from the stack. If we want to use a value that's later going to be available to the program, we need to make sure that we make a copy of it before we use it in an operation. Duplicate 1 duplicates the element on top of the stack. There's duplicate 1 through 16, just like the swaps, which will duplicate anything through the top 16 levels of the stack. So now that our counter is safely duplicated, we can start using it in the conditional part of the jump. We're pushing 4 on because 4 is the address of our jump destination. And then we get down to jump I. This is the conditional jump. At its essence, it performs just like the previous jump does, but it takes in 2 arguments. And the second argument it takes in is the condition. And it's fairly simple. You're not taking in a binary, you're not taking in a conditional function or anything like that. You're just checking whether the condition value is either 0 or not. In this case it's 1, so it's not 0. And if it's not 0, the conditional jump continues to jump. So we end up back at instruction 4. From there, the program continues forward as it did before, bringing the accumulator switching the accumulator into context, adding 3 to the accumulator again, bringing the counter back into focus, decrementing the counter, then getting back down to doing our jump again. And now this time, because the condition is 0, the jump knows that it shouldn't jump, and we can exit the loop. And now that we're out of the loop, we have to do something with that counter variable because it's not going to be useful outside of that loop. So we use a pop to remove it from the stack and deliver it to node. So all that swapping and duping is great fun to try and figure out in your head, and having them usable in the top 16 elements helps with trying to make programs that work. But programs get extremely complicated extremely fast. It would be helpful to have somewhere other than the stack where we could put other variables, say when we have more than 16 of them in a function. And for that, we have memory. In the stack machine, you have random access memory available to you, and you've got two commands for dealing with it. You have mstore to push a value into memory, and you have mload to pull a value from memory. So we'll take a look at an example of that. First off, we're going to push two values onto the stack, a 0 and a 2. 0 is going to be the address that we want to store to, and 2 is going to be the value that we want to store. And those are the two arguments that the store command takes. It consumes those arguments and writes the value into the memory slot 0. Given that there is a large amount of memory available, you can write until many different memory slots adjacent to each other. So we can set up another set of arguments and move through store again and put another value in memory. They don't have to be adjacent. This is an array of slots that you can put data in to be stored, and you can choose wherever you are pleased to go.
So is there only 255 or 256 slots?
There is 256 to the 2 slots.
Okay.
Yes. There's reasons why you don't want to use all of them, but we'll get to that.
Okay.
Yeah, I've made a mistake there, haven't I? No, I haven't. I haven't, because the words on the stack are 256 bits wide, so it's still got the right address space for that.
Or are they each 1 byte wide?
They're all 256 bit wide.
Okay.
This is important,
All right.
but I'll get to that towards the end of the talk. So storing stuff's all well and good, but it's not much use unless we can get it out again. So we push on a value to be consumed by the load. This is going to be the address that we want to pull back out of memory. And then mload can pull that back out of memory. Notice that it hasn't wiped that slot of the memory, so I could load repeated versions of that value onto the stack. This sort of does the same thing as our duplicate was doing before, but we have a constant reference back to what we were duplicating rather than having to shuffle the stack around beforehand. And this lets us change the way that we were doing the previous loop work. It changes the way that we were working with the previous loop and avoids some of the dancing that we need to do. So on the left here is our previous version of the loop, and on the right is the new version that uses memory. And there's not much of an optimization that you'll see here, but in a more complex program, the optimizations do appear, and here it's just nice to work through it and get familiar with the advantages you can get out of being able to handle memory this way. So stepping through the changes, first of all, we initialize both the counter and the accumulator again, but unlike last time, we're going to push the counter straight onto the stack. We're going to push the counter straight onto memory, so it's stored safely up there, and we don't have to context shift to and from it. The jump destination gets set up as before. Given that the accumulator is now the only thing that's living permanently on the stack, we no longer have to shift in and out of context for it. We can just add straight to it. And given that the counter is now coming from memory, rather than swapping back to it and duplicating it, we instead load it from memory in instructions 11 and 13, perform our subtraction against it, and then push it back into memory in instructions 15 and 17. Rather than duplicating, we just load the value again, and then the jump with its address consumes as much as it did before. That progresses around again until eventually we exit the loop in the same way as we did previously. Unlike what we did previously, we don't have to do any cleanup. The memory doesn't have to be wiped at that point unless you're being an absolute pedant about it. Given that it's random access memory, it will wipe itself at the end of the transaction. So that's the last deep dive into how the stack works, and I hope I didn't bore people too much with that and people kept up with me. Let's now look at how that mental model applies to some of the way that Ethereum utilizes this type of machine, and some of the design decisions that were made around both the machine and the Ethereum landscape with the abilities that are given how this machine operates. So first of all, let's look at why they chose a stack-based machine at all. And probably the most compelling reason was simplicity. All of the instructions all the operations which are available on the stack machine are very simple and straightforward in concept. They have very limited scope in what they can do. And there's also all of the componentry that goes into this virtual machine are also very simple. The memory, the operations that consume from the operations all consume directly from a stack and return to it. The operations install values in memory in a simple way, and the operations that can touch the environment are all very limited in what they try to do in a single operation. So implementation of a machine that's based on this spec can be very incremental and can be very can be more simply verified. And compared to a traditional register-based machine, the small operations are much easier to test and much easier to assess. Second big reason is measurable computation steps. In a traditional register-based machine, operations will have to operate against different types of memory. They will have massive compound operations occurring. It becomes hard to get consistent performance and consistent effects out of some of the operations, especially in the ways which they can be misused, or the ways that misuse is probably the wrong word, the ways which they can be reused. By separating all the data manipulation from the operations, we can get very consistent profiles around every operation that can be performed. We know the cost of pulling something out of memory. We know the cost of adding two things together. And we don't have to worry about those two concepts being mixed together or what side effects they might have on each other. Next big point was space saving. On the blockchain, you want to keep your payloads as small as possible if you can. So any way you can save space is a good thing. If we were looking at a traditional register-based machine, we would almost certainly have fewer instructions in a program, but because it's addressing registers rather than always addressing the top of the stack, you need to feed every single operation a set of addresses for it to work with. This results in much wider opcodes that eventually, which in almost every case end up being of a larger size for an equivalent program. By being able to break up the logic into smaller parts, you can eliminate the wastage of having to zero pad addresses, or of having to sub in false values into addresses or into operations. Much like the first point, the stack-based machine leads to simpler compilers and interpreters. Given that the Ethereum community is trying to be open and we are trying to have people implement their own languages, we're trying to have people implement their own computing nodes, we need the language developers to be able to write compilers that all end up writing correct EVM code, and we need the nodes to be able to interpret that EVM code in a consistent way across all of them. And having a simpler machine with a simpler instruction set makes this easier for developers. If they all had to try and re-implement Intel's errata for the x86 architecture or something, I think they'd all be lost, and we'd have far fewer people participating in the landscape. And the final point I'm going to visit on for why is that the stack-based machine is easier to optimize for than some of its alternatives. Given that everything is broken into very small chunks of functionality, trying to find patterns that you can reorganize to rewrite to be running faster is simpler than if you were trying to do it on a register-based machine, where many more side effects have to be considered before you replace a given set of operations with another. So that's enough reason for why they chose to use a stack machine. Let's look at some of the choices they made about the stack machine's implementation to tailor it to use on Ethereum. The first big decision they made is that the words on the stack are 256 bits wide. This is important for Ethereum because we deal with a lot of larger values, such as addresses and things, which are all upwards of 160 bits. If we committed to a 32-bit or a 64-bit architecture, then we would have, when we are faced with things like a 256-bit address, it would have to be done, any processing of it would have to be done in multiple stages across the entire word. By deciding that we are natively going to try and deal with values like this, we can try and optimize for it outside of the nodes and take advantage of future technologies rather than limiting ourselves to existing hardware architectures. Second decision they made is that the stack can only go 1,024 elements deep. And this is kind of twofold in its utility. Firstly, it prevents any attacks where people are going to try and dump data onto the stack to overflow the memory of the host machine, which would be bad and be an attack vector on the entire network. And secondly, it simplifies the implementation of the stack machine because you only have to find about 32 kilobytes of high-performing memory, which is much easier for people to do on various different architectures than, say, if you had to find multiple megabytes on a small chipset. Third decision they made was to make the system Turing complete. They didn't necessarily have to do this, but they did throw in all the operations that you need and all the memory access that you require to pass the Turing completeness test, which means that you can write any program you please on top of this on top of the Ethereum virtual machine. They might have had, there was an option where they could have decided not to make it Turing complete to try and enforce termination of the programs that were written on top of this machine, but they've obviously gone with the idea that versatility in the programs that are being written is more important than being able to limit them, and went with other measures to control people from being able to create non-terminating programs. And they made the whole system sandboxed. There is no general I/O, there is no network communications. You cannot access the host's memory. All you can do is access the components described inside the virtual machine and read from the world state that already exists. You can pass messages between contracts, but again, that's all within the virtual machine and the world state. So, that's the general sort of some of the general sort of decisions they made around the machine. Let's take a look at some of the decisions they made around memory specifically. And we've got two kinds of memory, and the first one of those is ephemeral memory. This is what we were using before. This is your random access memory. You access it through the mstore and the mload commands as we used earlier, and it's an array-based set of 256-bit slots that you can put your data into. And probably the most important thing to keep in mind when you're using it is that it's contiguous. So if you go to put something in address number 7, addresses 0 through 6 must be allocated whether they're populated or not. Otherwise, address 7 won't be reachable. Thankfully, you don't need to do this allocation by hand, though. That's done for you on your first write to a given address. The other type of memory we have is the persistent storage. This is accessed through sstore and sload. This is the storage which lives on the blockchain underneath a given account, and this is implemented as a key value store. Utilizing it inside of the stack machine feels very much like you would use the ephemeral memory, but the implementation means that you don't have to have a contiguous set of memory. So if you write to two different addresses that are not adjacent, it's not going to allocate anything in the middle. It's just going, because it's a key value store, it will only do the addresses which you specified. Excuse me one second. So this storage gets written back to the current account storage, and then is available to the future transactions being performed by this contract. The ephemeral memory disappears at the end of this transaction and will not be available in the future. So, persistent memory versus what you need just for this run of the program. The next big concept we should probably talk about is gas. Gas is the control mechanism that is used to make sure that people don't unduly abuse the Ethereum network. And they use it to control some behaviors such as preventing infinite loops because you consume gas, because you don't have unlimited amounts of gas available to each operation, to each transaction. And they use it to control abuse of system resources like memory, so you can't go and consume everything all the memory that's available on the host. And it also proves to be more flexible than just having arbitrary limits, because if Italy had come in and said that we're going to give you 200 kilobytes of memory and that's all that's going to be on Ethereum, that's going to change the way that people have to write programs and limit what they can do. By letting the developers make the decision about trading off the expense of the computation versus what they're actually going to use, it leads to more versatile uses of the system. So gas is paid per transaction in advance, and this is something that I hope that we're fairly familiar with. You can't just run away after submitting a transaction and hope that you never have to pay for it. And thankfully, the unused gas is refunded at the end of the transaction, so you can overcommit to what a transaction means. Every single transaction has a base cost of 21,000 gas applied to it before it gets to doing any computation, and this ends up being the base cost for a external account transaction. And then we have an additional gas cost, which is calculated per opcode that goes through the virtual machine. And this is where the predictable nature of the operations becomes super important, because we need to be able to put a static price on each opcode, which is exactly how the virtual machine determines how much gas is being consumed. Every opcode has a price. So let's take a look at some of those operations. So for something as simple as adding two numbers together, it's real cheap. It's 3 gas. All it does is grab off the stack and puts back on the stack using a very simple piece of arithmetic. If you've got slightly more complex arithmetic like multiply, from first principles, a multiply is a series of adds on a computer, but in almost every modern hardware architecture, it can be done in a single operation on the CPU. So it's recognized as being not substantially more expensive than an add, but slightly more expensive because it's slightly more complicated. And then you have things which start to get substantially more complicated. For example, an operation is provided to calculate the SHA-3 of an address. This is something that's provided as an operation because in Ethereum we do this fairly often. And on a lot of hardware architectures that are out there today, there's hardware optimizations to help you do it. So it's recognized as being more expensive than basic arithmetic, but not hyper expensive. Where you start to get a bit more expensive is where you start interacting with the world state or back with the blockchain. And say you want to look up the balance of an account, which is provided as an operation, that's 400 gas because it has to go and scan through the world state and make sure that it's been fully formed for the account that you're trying to query about. And then memory is the next part where it starts to get particularly complicated. For the ephemeral memory, your writes are still pretty cheap. They're 3 gas. It's not really any more expensive than writing onto the stack. But the allocation expenses start to get really expensive. Those are calculated by a function that figures out a cost based on how many addresses you've asked to be allocated. So if you're asking for 3 memory addresses to be allocated, it's still fairly cheap. But note that function is exponential. It goes up real fast. If you want an entire megabyte of memory, you're paying about 2 million gas to allocate it before you even start using it. So there is a compelling reason for developers to try and limit the amount of memory that their contracts are required to use. Loading back from memory, like writing, really cheap. It's expected that this will be that on every architecture that someone tries to write this for, it's going to be an easy operation. Persistent storage is more expensive yet again. Given that this is writing back to the blockchain and then you have an expectation that all the other nodes are going to have to clone the data that's written back, they charge substantially more for it. And because the read has to go and examine the world state and make sure that it's fully formed, it's also more expensive than the random access memory. Okay. So that's gas. The EVM keeps track of the gas consumed as it executes each operation, and the amount paid is proportional to the amount of computing effort expended. Moving on from that, so far we've been talking about transactions acting on single accounts and single bodies of code, but Ethereum consists of many different contracts and accounts that the EVM lets us communicate in between. So let's examine that a little bit. Our contract through the EVM can dispatch messages out to other accounts on the network, and these messages can target external accounts to do transfers between them. They can target and invoke other contracts, and they can create new contracts by supplying bodies of code. And they can also send messages back to themselves to create a nested closure for doing computation inside of. They can also do another type of message, which is self-destruct, which schedules the current account for deletion, which is good, because eventually we want to clean up what's living on the Ethereum network, or clean up what's living on the Ethereum blockchain. Like all other operations on the EVM, these contract communication parts are all governed by the gas which they consume. Doing a call to another contract is a flat 700 gas, but the story doesn't end there. The child contract that you call needs to have a certain amount of gas available so that it can perform its computation, and the amount it's provided is 63/64ths of what the parent has available to it. And because it only has a large portion of the available gas assigned to it rather than all of it, this recursively gets smaller the deeper your calls go. So by the time you reach a couple of hundred layers of contracts deep, you have almost no gas left unless your original budget was astronomical. Nope, back one. Great. Creating a new contract because you're writing a body of code to the blockchain is 32,000 gas. It's a fairly predictable operation in its scope, so it's a flat cost for that one. Self-destruct starts to get really interesting. The way that it is priced is to incentivize and discourage certain behaviors. So to invoke a self-destruct and get rid of your account, it costs you a flat 5,000 gas. What else has gone on in your contract then affects what happens after that. Immediately, you'll get 24,000 gas refunded to you and added back to your transactions counter. So self-destructing should earn you gas. But if into self-destructing you went and created another contract for an evolving version of a piece of code or something to that effect, you get charged an additional 25,000 gas, which ends up being a net cost to you. So it incentivizes people to clean up the blockchain and remove data, but if they see you adding more data again, you won't really clean anything up and they will charge you anyway. So this is a whole lot of moving components inside this machine, and as with most machines, not everything always works properly. So let's look at what happens when it doesn't work right. And when it doesn't work right, you have exceptions that are thrown. And these are always due to either a piece of bytecode which can't be interpreted by the virtual machine, or an illegal use of a virtual machine component. When an exception happens, the person who invoked this transaction loses all the gas which they committed to it, which is rather mean to most users, but it's up to users to make sure that they aren't asking for things to happen that result in crashes, and it's up to developers to write contracts in ways which aren't so punitive to users. There are various mechanisms which are starting to coming into the virtual machine that let you avoid charging users the entirety of their committed gas. So the types of exceptions that you're likely to see, first of all, an invalid jump destination. If you manage to jump to an ad rather than a jump destination, the virtual machine is going to figure that your train's gone off the tracks and tell you that you should probably shut down instead. Out of gas exception. Given that you only have a finite amount of gas on each transaction, eventually you're going to run enough operations that you'll consume all of it. And at that point, the virtual machine just tells you to bugger off and throws an exception. Invalid instruction. So the instructions that are read by the EVM are 1 byte wide, but there's only about 127 instructions currently defined, so there's a whole lot of space there inside that 256-bit byte where you can feed instructions that the virtual machine's not going to understand. And if it sees one of them, it doesn't know how to respond, and it tells you to go away. Call depth. If somehow you do manage to commit enough gas that you are able to go all the way down to 1,024 level of contract calls, it's going to stop you from going any further because it figures that you've been abusing the Ethereum network at that point. And then there's address collisions. Given that you can create accounts at a given address, there is a potential that there's already going to be an account at that address, and if that happens, it's an exception. Luckily, you can go and check whether that address is available before you go and do the creation. So, in the description of this talk, it mentioned that we were going to look at how Solidity code gets run on the EVM, so I probably should cross that bridge before we get to the end of the talk. So we're going to take a quick look at this very, very basic Solidity contract. This stores a counter that we can get the value for, and it just adds up by 1 every time it gets touched. To get this into a way that the EVM can use it, we run this through the Solidity compiler. I'm not going to go into what the Solidity compiler does. There could be many more talks about how compilers transform code and do optimization on it. But we are going to take a look at what the output of the compiler is. So after you run through, you get this binary byte stream. And I can't read that, and I'm not going to try to. Some people try to, but I don't envy them at all. What I do instead is I run it through a disassembler to transform that back into opcodes. And now suddenly that's something that looks familiar to us from half of this talk. There's parts in here that we haven't visited on, like call value here, which is how you get information out of the transaction that called your contract, or revert, which is a way for you to cheaply exit this contract without causing an exception. But everything else there is now something we can reason about. We can look at this and see that data is getting pushed around, and they're shuffling values to be used in different computations. And we can start to reason about how that compiled program consumes gas and ends up being something useful on the EVM. And that simple little contract that we had ends up compiling to 210 instructions. And there's some stuff in here that we wouldn't necessarily expect to see from the Solidity code, like we've got, nope, didn't quite make it on the slide. There's conditional logic further down, but there was no conditional parts in the Solidity contract. Except that there really were, because the EVM isn't aware of the concept of functions. So the first thing that happens when it enters into the contract is it needs to figure out which function you want to call, and it uses conditional logic to jump to executing the right function. So this leads to the idea that Solidity is a higher abstraction of what is available to be done on the virtual machine. And everything which you could do in Solidity, if you look into it, you can transform into these opcodes and have an understanding about how it's going to be executed, exactly how much gas it's going to consume, and what sort of performance profile it's going to have out there in the wild. So, after all of that, I hope you're a bit more familiar with how the EVM works and have a bit of a mental model that you can start applying other Ethereum concepts on top of. And we've looked at how data flows from one instruction to the next and how memory is used. We've looked at how gas affects the execution of this. And we've looked at what sort of things can go wrong with the code. And I like to have this sort of mental map available to me so that when I do think about why Ethereum was designed in a certain way, what are they taking advantage of and what limitations of their implementation are they trying to avoid? And we can answer questions like what really is happening when we ask to do a token transfer. So again, I hope that was all helpful and you do take something away from this, and even if you never look at bytecode in the EVM again, I hope it gives you a more realistic basis for some of the Ethereum concepts. So thank you. Yep, questions?
So there have been some reports in the popular press about concerns about isolation of the memory data associated with smart contracts. We also know that people can write arbitrarily bad code in smart contracts and do even unintentionally. This has led to some concerns that it's dangerous to lock up a large amount of ETH, say conditionally, in a transfer that might only take place under certain smart contract conditions. Right? So say I want to lock up thousands of ETH, which might be millions of dollars, and that might sit there for some years until the appropriate conditions are executed. And so these little hints that we get of isolation problems, either in memory or access to that memory, or code or access to that code, have left us in a position where we're advised not to write those kind of contracts. Do you, or does anybody else here, have enough information about where those vulnerabilities are in the current implementation?
I'm far from an expert on this, but I don't, from my knowledge of the way the EVM is set up, there isn't a vulnerability there. There is definitely the potential for vulnerabilities of memory sharing in the implementations such as Ethereum or Go Ethereum when they've written their virtual machines. And I think the way you would avoid such attacks having a massive impact on the network would be through a diversity of different implementations all addressing the same data. Given that every transaction gets executed by every fully populated node, if they aren't all reaching the same answer about should those conditions be met or not, then there's going to be a fork that happens at some point because one of them is going to throw an error about it. And that would hopefully be the early warning sign that someone's found a massive exploit in one of the implementations and tried to do this. But yeah, that is not an area that I've explored very well at all.
Thank you. So as far as you're aware, it's not a design issue, it's an implementation issue.
Yeah, the design as it exists, aside from the persistent storage, which should be locked up behind that account's private keys anyway. There is no parts of the design which should lead to leakage of the ephemeral memory. I would entirely expect that to be a node implementation issue rather than a spec issue.
Yeah, well, the ephemeral memory, is just temporary. It's just for the execution of a transaction, so it will come and go. You're talking about the account state and somehow or other reading account state from one account to another account. So you're within a contract and reading values from a different contract or something like that.
I'm not actually. I'm talking about having a contract which locks up ETH.
Yeah.
and transfers on condition. And the advice that we were given was, don't do that yet. We hope to fix some security bugs in the next half a years. And I don't have any more knowledge of what those security bugs are. I presume they're isolation-related issues, but I don't know.
I think Chris is right. It's going to be an implementation thing. So I guess as we have more Ethereum client implementations, such as Pantheon client, launch date October 30, then you'll have more diversity. So say if one of them had a bug, a software bug, as you're saying, Chris, then it would have less impact because it wouldn't be able to get consensus.
But Mike, if most of if you can get 51% of your miners saying, I'll write a get or something, then you still have the same problem.
True. So what we need is a big proportion of them to be running Pantheon. How's that for a good idea?
I guess there's the issues that people are seeing in smart contracts where there's like reactancy logs and those kind of things in the actual contracts themselves, which may be where there's concerns. Maybe that's where some of the reasons not to not get ready for a long time is people always think of one way to protect the code in that way rather than have the actual EVM implementation or the EVM sort of stack base aspect of it. I guess that's probably where I would be nervous. Every time there seems to be issues in smart contracts, with lots of money involved. Well, every time there's a smart contract which has lots of money involved with it, you hear about breaking it. There's a lot of incentives.
Right, and so right now we're working around that with out-of-band business arrangements, and we would love not to be.
Yeah.
Is the gas price of those operations set, or will they be updated?
The gas price of those operations is set for a given, what's the word I'm looking for? It can be adjusted at hard forks of the network.
Right.
But that's the cost in gas. There's also the other concept of gas price that translates that gas into the Ethereum cost. That one does float over time, and that's how you influence miners to pick your transaction over other ones by paying them more. But yeah, those are set for a given period on the chain, and it takes a hard fork to change them.
Right.
I've got a question. So, in the various ways that you could throw an exception, most of them seem to be there's a bug in your code. So you're going to an invalid jump address. But the running out of gas is very much a user error. So you're thinking, all right, my understanding is it's going to use maximum of 20,000 gas or 30,000 gas. So you run it, and then it goes pop and blows up on you because it does more than you expected. Do you have any thoughts on why they would have put in something like that? So because they seem to be very different problems, and I guess even running out of stack is again potentially an execution issue rather than there being a bug in the code.
Yeah, I don't see them as being different problems because the exceptions are trying to address the VM does not understand how to react to this situation. And whether that's you've done a jump to somewhere that you shouldn't have or you've run out of gas, there's just no logical answer the VM can use to respond to that.
Mm-hmm.
So it needs to say that I can't process this transaction any further. And then looking through the yellow paper or other specifications, it describes what to do in response to those. And the answer almost invariably is take all the gas that was made available to you and then tell the user that transaction failed.
But then what's the difference between, if you do a revert, that doesn't cost you anything. And
no, not quite. A revert does cost you something. Revert says whatever gas has been used so far, I have consumed that gas, but now I'm exiting the contract without further cost.
Oh, okay.
So a revert, that revert was, 15 instructions in or whatever. It's still going to charge you for those first 15 instructions, and it's going to charge you for the 21,000 base cost.
Okay.
Does kind of part of my question was if you're in the Solidity code throwing an exception for an invalid state of your actual contract, does it also forfeit all the committed gas, or is it like a revert?
This one I'm not entirely certain on because I only very briefly touched on it in my readings. But you've got 3 different ways to tell a Solidity contract that something's wrong. You've got, first of all, the traditional throw, which does do one of those types of exceptions, I believe, and does end up forfeiting. And then you've got 2 others which are more recent. First one of those is assert that checks a condition, and the second one is revert. And both of those use the revert opcode to do an early termination of the contract without charging any more gas. Because originally, way back when, the idea was meant to be that someone tries to execute something and your way of terminating earlier was you did something illegal to the VM. You would do a jump to an illegal address or something like that. And it was seen very much as being punitive to the user. So I don't really remember which hard fork it was at because I haven't done enough reading on that. But at one of them, they introduced revert and the cheaper ways of letting users out of those commitments because it just made sense for the programs to be able to do so in conditions which they deemed correct.
So if you do charge gas on a revert, which you're saying you do, that means though that decrease in that account's amount of ether due to it having consumed some gas has to go, be pushed across.
Yes.
So it's got to be mined, the fact that you've had a bad transaction.
Yes. The transaction still exists and completes because operations were done against it. It's like miners out there at the moment. They look for transactions that are going to fail so that they get more gas out of it. Because they still record that the transaction came in, and I tried to process it and did through an exception. And that ends up being recorded on the block this transaction was requested, and then they take the gas that was provided for it. In the case of a revert like that, they run the transaction, you do the computation, absorb the gas that you did take, and refund the remainder. And that ends up being a transaction the blockchain just as any other, even though it may not have resulted in because it's a revert, it almost certainly didn't result in any any productive things being done on the blockchain. But yeah, it doesn't at all subtract from the fact that computational effort was expended, and someone should pay for it, and will get paid for because it still ends up being a transaction.
Okay.
Yep.
Also with regards to the base, like 21,000 gas price, where's that actually enforced? Is it when you're submitting the transaction, or is it when it's like at the VM level?
I am honestly not. I don't know. Adrian has an answer.
It's part of the intrinsic cost of the transaction, so it's charged to the account before your transaction starts processing.
Okay. So when it's like ending.
No, so it's only when it's mined into a block. But the first step before you actually launch into the EVM, as with processing any transaction, is to charge the intrinsic cost, and then you run through the EVM and then you do the refunds again.
It's part of the stack.
Yeah.
So it wouldn't be possible, or would it be possible that you could submit a transaction with less than the minimum gas price?
You could do that. Most likely the transaction pool will quickly look at it and go, that's not going to execute that cost.
Okay. And that's like a client implementation.
Yeah, there's no reason that the client couldn't accept the total limits transaction tool and then when mining it could try and put it in the blockchain.
Well, most clients probably would try and do that, and if it only had 5,000 gas on it, that's a free 5,000 gas.
Well, if you don't have the intrinsic, you can't end up processing the start.
Or at least you shouldn't start.
But
if it's just free gas. Sorry?
It wouldn't be a valid block if you did, so it wouldn't validate.
Okay.
Yeah, so I'm a little bit easy on that, but I'm pretty sure if you don't have the intrinsic cost, you can't put it into a block, you can't put it into a block size, it wouldn't be.
Adrian probably knows better about that than I do, so I'll take his answer. Any more questions about anything? Cool. Thanks for coming. I'll hand back over to Peter. There's the dates that Peter wants.
So as you can see, we've got a whole stack of things coming up. So Lucas Cullen, who is not in the audience at the moment, but will be standing here hopefully in 2 weeks' time, is going to tell us all about Viper. And then Brett Henderson, who's somewhere here, just stepped out, is going to tell us all about Ethereum 2.0 in 4 weeks. And Roberto Saltini is going to fly up from Sydney and tell us all about zero-knowledge proofs and Zcash. And then I am going to have an implementation of the decentralized PRNG by October 30. And so we're going to have some Solidity code
and it's all going to work. Etc., etc. Actually, this one here, the October 17th, is a very interesting one. So we kicked around what should we talk about, and so these days we don't talk about the internet or, you know, like what we're going to do, all the applications. You know, it's just background noise now, isn't it? So the idea of post-blockchain world is when Ethereum or things like it are just part of the background noise, and we're in 2025 or so, and this is just part of the environment. Where are we up to? What does it look like? What could we be doing? What are the things that we should be thinking about? And what would the landscape look like? And I can't remember who we said was going to talk about that or how we're going to do it, so that'll be interesting. And then current research, UQ, QUT and Griffith Uni, and I've got to get around to talking to people to get some speakers for that. So anyway, thanks for coming everyone, and see you in 2 weeks' time. Bye-bye.